Greetings. Welcome to today's session. Today we will get started with our discussion on loop flow. So this is a very useful technique to design closed loop control system and also to figure out the controller parameters that will ensure both closed loop stability and closed loop performance. Okay? So that way it is pretty useful. I will give a brief recap of what we discussed in the previous lecture before we take it forward, right? So by now we are familiar with the standard form, like of the closed loop negative feedback system that we analyze. The block diagram is as given here. So the closed loop transfer function is going to be g of s by 1 plus g of s h of s. As a premise, we start off with the what to say, sort of like assumption, right, that we would be able to write the open loop transfer function in the form shown here. Okay, so this is a premise with which we start the discussion on root locus. That is, we should be in a position to write the open loop transfer function as some k times s plus z1 all the way till s plus zm divided by s plus t1 all the way till s plus tn, where k is some real number and minus z1 through minus zm are the open loop zeros and minus p1 through minus pn are open loop poles. Okay, given the question that we ask ourselves is that, like, how would the closed loop poles, like, change as we vary k? Okay, so that is the question which we answer by discussing about root locus. Okay, so that's what we are going to do. And typically, this k is a design parameter, like involved in the control design process. So that way, like, we will be able to figure out, what ranges of that parameter k will result in both closed loop stability and performance. For example, we sort of like reduced closed loop performance into a sub-region in the left of plane, right? Like what we did a few lectures ago in this example. Considering this example, if we are able to place all the closed loop poles in the shaded region, right, feasible region indicated here, then not only will the closed loop system be stable, the closed loop system will also achieve the performance metrics that we have been given, right? So that way, it is pretty good. Okay? So that, like, we are able to achieve both stability and performance, and we, at the same time, we are able to figure out what ranges of the design parameter will satisfy both. Okay, so that way, root locus is a very useful technique. Okay, so as we go along, we will see that we will be able to visualize, okay, the various closed loop poles and their evolution with respect to k. Okay, and we will be able to get ranges of k, which will help us, place the closed loop poles in the feasible region as we have shown there, right? So let's start our discussion. So as we know, the closed loop characteristic equation is 1 plus g of s h of s equal to 0. Okay, that is the closed loop characteristic equation. So if we look at this closed loop characteristic equation, we can immediately rewrite this closed loop characteristic equation as g of s h of s equal to minus 1. Okay. So what we have done is that we have just taken 1 to the other side. Okay, we have not done anything more than that. Okay, and one way of interpreting this equation is that the values of f that satisfy that make g of s h of s equal to minus 1 are the closed loop poles, right? And what is g of s h of s? It is the open loop transfer function. So now slowly we can see why we defined a quantity called the open loop transfer function, which is g of s h of s. Please note, once again, I am reiterating that the term open loop transfer function is associated with a closed loop control system, right? The transfer function of an open loop system is a different entity altogether. Okay, so please note the subtle difference between the two quantities or the two terms. Okay, so the values of s that essentially make g of s h of s to be equal to -1 are the closed loop. So the term open loop transfer function is associated with the closed loop system. Please remember that. Okay, so any value of s that results in the value of g of s h of s being equal to -1 are the closed loop. Now, please note that g of s h of s is a complex valued function of s. So see, s is a complex variable. So you take any open loop transfer function, we can give any complex value of s, right? So the resultant value is going to be a complex number, right? So that's why I mentioned that g of s h of s is a complex value uh, function. Okay, so if we plot what is called as the g of s h of s plane. Okay, that is, we are considering, I'm labeling the complex plane by either S plane or G of S, H of S plane or some other label to indicate what is being plotted. Okay, so that is what, so when we label what is called as a S plane, we are plotting the values of it. Okay, so that is something which is subtle and we need to understand, okay, from the context. So if you look at this point -1, okay, in the g of s h of s plane, -1 is going to be here. Okay, so if we recall the graphical representation of a complex number, right? So typically what we do, we draw an arrow, right, from the origin to the particular point, and the length of the arrow is the magnitude, and the angle made by the arrow with the positive real axis will be the angle, okay, or the phase. So in this case, we can see that the magnitude is 1, okay, the length of arrow is 1, right, and the angle can be taken to be plus 180 or minus 180, okay, depending on how we are looking at it, right? So if we go counterclockwise, it is positive, clockwise means it's negative. That's the convention. Okay, so consequently, we can see that the point -1, okay, in the complex plane has a magnitude of 1. Okay, if we treat -1 as a complex variable, it has a magnitude of 1. Okay, and it has a phase or angle of 180 degrees. Okay, and this is a periodic quantity. So when we evaluate it, we are going to look at it as plus or minus 180 degrees times 2k plus 1. I will tell you why we write it like this shortly. K taking the value 0, 1, 2, etc. Right? The reason is that, like, see, I know that, you know, if I go look at -1, I know that I am going to arrive at -1 by taking an odd multiple of half rotation. That is, if I travel, okay, from the positive real axis, okay, if I draw an arrow from the positive real axis of unit magnitude, I rotate it by odd half rotation or odd multiples of 180 degrees, either way, plus or minus, I am going to come to -1, right? So that's why we take it as plus or minus 180 degrees times 2k plus 1. Okay, k taking the value 0, 1, 2, etc. So that is the implication, okay, of this particular expression. Fine. Okay. So now the point is the following, right? How are we going to use this, right, in our analysis? So once again, please stop me anytime you have a question. Okay. So I'm just using results from complex variables. Okay. That's all I'm doing. So now looking at the equation g of s h of s equals -1, which is the closed loop characteristic equation written in a different form, we will see that we can rewrite the equation g of s h of s equals -1 as two equations. The first one being the magnitude of g of s h of s equal to 1, The second one being the angle or the phase of G of S H of S being equal to an odd multiple of 180 degrees. Okay, so we are going to write that plus or minus 180 degrees times 2k plus 1, k equals 1, 2, etc. Okay, so the first equation is what is called as the magnitude condition. Okay, the second equation is what is called as the angle or the phase condition. Okay, so these are the two conditions as we can see here. All right. So what is the connection? Once again, let me repeat. The closed loop characteristic equation is 1 plus G of S H of S equal to 0, right? So we rewrite that equation as G of S H of S equal to minus 1. And so consequently, since we know that minus 1 can be written or visualized in terms of its magnitude and phase as we discussed here, we can rewrite this equation G of S H of S equal to minus 1 as two equations. That is, the magnitude of G of S H of S being 1, and then the phase of G of S H of S being an odd multiple of 180 degrees. Okay, so we get these two conditions: the magnitude condition and the angle or the phase condition. Okay, so the implication. What is the implication? The implication is that, like from what we have discussed. So what we have done is that, like we have written that 1 plus G of S H of S equals 0 as two conditions. Okay, that's all we have done. But these two conditions involve the open loop transfer function, C0. So the implication is that any value of S, the complex variable S, that satisfies the magnitude and the angle condition, okay, angle condition or close to loop. It's a closed loop. Okay, so let's say use simpler terms. So any value of S that satisfies these two conditions is a closed loop form. Okay, so that is the consequence. Okay, by writing. So now the bottom line, like is that can we utilize these two conditions to come up with a method by which we can plot. Okay, so going back to our question, okay, how do the closed loop poles vary? Okay, as the parameter k change, what we can say is that the visualization of the same. Okay, now that we have discussed this, okay, it's called as a root loop. The graphical visualization, okay, to be very precise. So it's called as a root loop. All right. So I hope now it is clear what is the root loop. Okay, so we are going to figure out how we are going to construct the root loop, okay? But at least from a what to say conceptual level, I hope I think this process, like it is clear, like as to what we are trying to achieve, okay, through this particular process, right? Okay. So now, having defined what is the root loop, like and having looked at the what to say the angle condition and the magnitude condition, the question that arises is that how do we now take this forward, right? So how do we get steps that can help us in constructing the root loop? So in this process, what I am going to do is that, like, I am going to explain the steps by considering an example. Okay, so let's write down the problem statement, and then like we will start solving it, and in that process we will learn the steps in constructing the root. So let us consider a plant whose transfer function is 1 by s squared plus 4. Okay, so this is the transfer function. So the question is, design a unity negative feedback closed loop control system such that it is stable, the closed loop system is stable and satisfies the performance requirements of the settling time being lower than 4 seconds and a peak overshoot less than 10%. Okay, so I'm just taking the same, performance specifications for which we had obtained the feasible region. Okay, so that like we will know how to do this problem. All right. What we are going to try out is essentially with a proportional controller. Okay. So we will first try to see whether a proportional controller works. If it can stabilize the closed loop system, well and good. What we are going to do is that, like, then we are going to see how we can use a root locus to do this. Okay. So once again, if we were to draw the block diagram, just to draw the block diagram before we go to the problem. So please note that I'm just drawing in different order now. Okay. So the system is 1 by x squared plus 4s. So this is u of s and we get y of s. So we have a reference input and we are dealing with unity negative feedback, right? So the feedback part, we have unity mapping, then we subtract and then we take the okay and pass it. Okay, so that's what we have. Then what we do is the following. So we essentially start solving the problem, right? So if I take the plant transfer function as such, right? So we are going to have plant transfer function as 1 by s squared plus 4s, right? So what are the poles of the system? So if I have the plant transfer function as 1 by s squared plus 4s,
0 and minus 4.
Very good. So they are going to be 0 and minus 4. So is the plant stable to begin with?
No, sir.
Marginally.
So yeah, it depends on how we want to visualize it. Yeah, we can say marginally or critically stable, but it's certainly not a before stable, right? So so we can see that like a step input will lead to the output becoming unbounded, right? So that's something we can immediately observe, right, by the presence of a pole at the origin. So let's try designing using a proportional controller. Let's C of s be Kp. So G of s is going to be equal to C of s times P of s, which is going to be Kp divided by s squared plus 4s. Okay, we know that H of s is unity. Okay, it's 1. So consequently, we will have the closed loop transfer function. By now, I'm sure we are familiar with this process. It's going to be G of s 1 divided by 1 plus G of s H of s. Okay, that's going to be equal to Kp divided by s squared plus 4s. The whole thing divided by 1 plus Kp divided by s squared plus 4s. Okay, so that's what we are going to have. So if we simplify, we are going to get Kp divided by S square plus 4S plus K. Okay, so that's what you have. Okay, so this is our closed loop transfer function. So consequently, the closed loop characteristic equation is going to be, let me write down the closed loop characteristic equation. The closed loop characteristic equation is S square plus 4S plus Kp is equal to 0. So when do you think the closed loop poles will both lie in the left of complex plane?
When Kp is positive.
So please note that this is a second order polynomial, right? As we discussed, the necessary and sufficient condition for this polynomial to be Hurwitz is that all the coefficients of the polynomial must be non-zero and of the same sign. Okay, so we can immediately we can even form the root array, right? So if we form the root array, just for clarity, we essentially put write S squared, S power 1, S power 0. The coefficients will be 1, 4, and Kp. Now in the S power 0 row, we multiply 4 and Kp, subtract the product of 1 and nothing, divide by 4, right? So we are going to get Kp, right? And if you look at the first column of the rows array, we have 1, 4, and Kp. 1 and 4 are positive. So consequently, for stability, we need Kp to be greater than 0. Okay? So this implies that the closed loop system will be stable for all Kp greater than 0. Okay, so that's something which we can immediately recognize, right, for particular from this particular derivation. Okay, so if I plot this so-called what to say controller parameter space, okay, here, so if this is 0, so we see that for all Kp greater than 0, the closed loop system is stable. So the feasible range of Kp is between 0 and infinity, okay, for stability. So the question is, like, okay, we have using this route criteria, we have essentially narrowed down the range of Kp from minus infinity to plus infinity, right? But however, the question that still remains is that how do we now go from here and get a smaller range, if possible, that will satisfy even closed loop performance. So, because if you recall, the problem statement that we have been given is that we need to design a proportional controller that satisfies both stability and performance, right, as far as the closed loop system is concerned. Okay, so then the question becomes, like, how do we get the corresponding range, like of controller parameters, that satisfies both. Okay, so now that corresponding thing is root locus. Okay, so now just for simplicity of notation, okay, for simplicity, okay, rather than writing the subscript p all the time, okay, let us replace Kp with K. Okay, so just the proportional constant with K. Okay, so then what happens? Okay, so we can immediately see that the open loop transfer function in this particular case, okay, which is g of s times h of s, is going to be equal to K divided by s squared plus 4. Okay, and of course K should be greater than 0 for closed loop stability. Okay, so that's something which we have already determined. Okay, so I hope it's clear what I'm doing, right? So now I'm going to consider the open loop transfer function and go ahead. All right, so please note that what to say, I have replaced Kp with K just for simplicity of notation, rather than write the subscript k all that kp or write the subscript p all the time. I've just done this. Okay, so immediately we can immediately see that as far as the open loop transfer function is concerned, the value of n is 2 and the value of m is 0, right? So if you recall, m is the order of the denominator polynomial of the transfer function n, okay, and m is the order of the numerator polynomial of the transfer function, right? So we can observe that here the denominator is of order 2 and the numerator is of order 0, right? So consequently, we can get the open loop poles and open loop zeros. The open loop poles are going to be at 0 and -4, okay, and the open loop zeros, there are none. Okay, there are no open loops. Yeah, as far as this particular system is concerned, right? So now the question arises, how do the closed loop poles vary with k, right? As we go ahead, all right? So let's start discussing the steps of the root locus. But are there any questions till now?
No, sir.
No, sir.
Okay, so let's start drawing the root locus. So what I'm going to do, sorry, not perfectly straight, but right? So this is the vertical axis, this is the horizontal axis. So I'm drawing the S-plane now, and marking. I'm going to mark the open loop poles, right? So as we know, the open loop poles are the poles are marked by X form, right? So that's what we have. So we have a pole at the origin, we have a pole at -4, right? So that's why these are the two open loops. Okay. Now the question is the following, right? How do we plot the locus of the closed loop poles, right? As k is varied from 0 to infinity. Okay, so that is the question that we have to do. So, how do the closed loop poles vary? In the S-plane, as k is changed from 0 to infinity. All right, so that's what we have. Okay, so if let's try to answer this question. Okay, so this process, okay, or this particular what to say set of steps constitute the construction of the root locus. So if you go to the drive folder where which I have shared already with you, and that also contains all the lecture videos. I would have also uploaded a PDF file by name root locus construction, right? So let me open it. So this is the file with essentially where we are going to learn all the steps, okay, to plot that are involved in plotting the root locus. Okay, so I am going to discuss the steps, along with the what to say example, right? In conjunction with the example that we are being considered. All right. So let me discuss these steps. So first is that let us of course, although these steps are for any generic system, we are going to essentially apply it over a particular example. So let's go through all the steps one by one. All right. So what is the first preamble to this particular construction of root locus? So let us consider a closed loop negative feedback system whose characteristic equation, right? As we already know, the characteristic equation is the equation whose roots are the closed loop poles. The characteristic equation in general is given by 1 plus k times s plus z1 all the way till s plus zm, and divided by s plus p1 all the way till s plus pm, right? Because the closed loop characteristic equation is 1 plus g of s h of s equals 0, right? So g of s h of s is k times s plus z1 till s plus zm divided by s plus p1 till s plus pm. Okay. Now we shall consider the case when m is less than or equal to n, which is our scope of our study, and with k being a positive parameter, which is the case in our example under consideration. In this particular system, minus z1 through minus zm are the open loop zeros, and minus t1 through minus tn are the open loop. So the root locus traces the evolution of the roots of this equation with variation in k. Okay? So that's the purpose of the root locus. And the root locus will have n branches or curves. Why? Because please note that the closed loop system will have n poles, right? Kindly remember that. Okay, because if you have a second order open loop system, the closed loop system is also of order 2, right? We would have realized this here, right? So our open loop transfer function is of order 2. You look at the closed loop characteristic equation, that is also of order 2. So we are going to have as many closed loop poles as that of the open loop poles. So consequently, the root locus will have n branches, okay, or curves. Now, the steps involved in following the constructing the root locus are the following, right? So, what is the first step? The first step is to locate the open loop zeros and poles in the complex plane. Okay, so that is the first step. So, how do we get at this step? Okay, so note that each of the n curves in the root locus will start from an open loop pole for k equals 0. Out of these, m branches will terminate, or m curves will terminate at an open loop 0 as k tends to infinity, and the remaining n minus m curves will go to infinity in the complex plane along a. Okay, point number 1. There are going to be n branches in the root locus, right? So that is clear to all of us. Why? Because there are going to be n closed loop poles, and consequently, there are going to be n roots to this equation, right? That we are considering. Correct? So if there are n roots to this equation that we are considering, then what happens? Like we are going to have n branches in the root locus, right? As we vary this parameter k. So that's why we have n curves in the root locus. Now the question is, how do the branches start from open loop pole as k equals 0, and then like go to open loop zeros as k tends to infinity, and some go to infinity. Why is that? Okay, so let me explain that, right? So let's go through each step one by one. So in general, the closed loop characteristic equation is going to be 1 plus k times s plus z1 all the way till s plus zm divided by s plus t1 all the way till s plus tn, okay, equal to 0. Right? Now we can process this equation as s plus t1 multiplied by s plus tn plus k times s plus zn all the way till s plus. Right? So that's what. Right? Is it not? So the point is the following, right? So if we have k to be 0, right? What will happen? This is the closed loop characteristic equation written as what to say a form wherein we have taken the LCM, right? And we have written. Now, if k equals 0, let us say we consider the case where k equals 0. What is going to have this happen to this equation? This is going to reduce to s plus p1 all the way till s plus pn. Okay, so this implies that the closed loop poles are the same as open loop poles, are minus p1 to minus pn when k is equal to 0. Of course, when k tends to 0. Okay, so see, it doesn't make sense to say k equals 0, because if k is equal to 0, like you see that we don't have any problem to solve in the first place, right? So we can make k to be 0, right? But slightly retuning it, we can say as k tends to 0, as k tends to very small numbers, the closed loop poles are going to tend towards the open loop poles. I'm sure all of us agree to. So now, if we go back, we can essentially mark these 2 points. So there is going to be one open loop, one branch of the root locus starting from k, the from the pole at open loop pole at 0 and one branch of the root locus starting at -4 as k tends to 0. Okay, so these are the starting points of the two branches. Okay, so I hope it is clear how we got this particular condition. So in this particular example, the root locus will have two branches. Okay, and the two branches, one branch will start from -4 and another branch will start from 0 because they are the two open loop poles. Okay, now going back to the same equation, the same equation can be written as 1 divided by k s plus c1. Now I am dividing by k, s plus c1 plus s plus z1 all the way till s plus zm equal to 0. Right? I'm sure all of us agree. Right? I've just rewritten the same equation by dividing by k. All right, on both sides. Now we can immediately see that 1 by k tends to 0 as k tends to infinity. We are considering the other extreme, right, of k. First, we consider what happens when k tends to 0. Now we are considering what happens as k tends to infinity. So now, if we can see that as k tends to infinity, what is going to happen to this equation? This implies that the first part will now vanish. We will have s plus z1 all the way to s plus zm equal to 0. Okay, so this is what will happen. So this implies that s equals minus z1 through minus zm are the closed loop poles as k tends to infinity. Okay, however, as we already know, we are considering causal systems where m is less than or equal to n, right? So that's the case we are considering. So even in the problem that we are considering, we have example problem we are solving, there are two open loop poles, but no open loop zeros, right? So consequently, if I have two branches of the root locus starting from each open loop pole, where do they go and end? Because there are no open loop zeros in the problem under study. That is why, if you look at the step 1, we say that the remaining n minus m branches or curves will go to infinity in the complex plane along what are called asymptotes. Okay, as k tends to infinity, we will deal with the process of constructing the asymptote in step number 3. Okay, which will come up. Okay, so now with this knowledge, let's go and read the step number 1. So once again, step number 1 is to locate the open loop poles and open loop zeros in the complex plane. So we have identified that there are going to be n branches or curves in the root locus, and each branch will start from an open loop pole as k tends to 0, and out of these m branches will terminate at an open loop 0 as k tends to infinity, and the remaining n minus m branches will go to infinity in the complex plane along as k tends to infinity. Okay, so I hope it is clear. So in our particular problem, there are two branches. One branch will start at 0 and another branch will start at -4. Okay, so that is the point. All right. Okay. So any questions on step number 1? Okay. Now going to the next step, let us say we consider this pole at -4, right? We are going to see, we are now going to reason out why or how the branch will start. See, if you consider the pole at -4, see, the branch of the root locus can start like this, it can start like this, it can start like this, like this. There are infinite possibilities, right? Isn't it? See, the only condition is that it should start at -4, but which direction? Okay. So now, if you look at -4 per se, it is only one single non-repeating open loop pole. So now the point is the following, right? Uh, it is that if you have an open loop pole which is non-repeating, we cannot have the root locus starting in any direction other than along the real axis. Why do you think that is the case? Let me repeat my statement. If you have a non-repeating open loop pole, the corresponding branch of the root locus cannot start in any direction other than along the real axis. Why not? Why or why not? See, let's argue step by step, right? So please note that we are dealing with a polynomial with real coefficients, right? Although S is a complex variable. What do we know about polynomials with real coefficients? About roots of polynomials with real coefficients? Suppose, let's say there is a complex root. What can you say about it? Is there a condition? Can you recall something about polynomials with real coefficients? So if you have a complex root, the conjugate also must be a root, right? Isn't it? So if we consider this pole at open loop pole at -4, suppose, let us say for the sake of argument, this is the branch, okay? We are with which we are starting, okay? So please note that we are going into complex, what to say, numbers, right? Then obviously the conjugate also must be a root locus, right? Branch, right? Why not? Because I can have just one branch, right? Starting from the real axis and going to the complex plane, right? Isn't not? The conjugate also must be a branch, right? Because of the fact that we are dealing with polynomials with real coefficients. Because once again, for polynomials with real coefficients, if we have a complex root, the conjugate also must necessarily be a root. Okay, so that is the condition or the fact that we are using. But however, how many branches can start from a pole? From an open loop pole? Only one branch, right? Can we have two branches starting from the same open loop pole, which is non-repeating? Certainly not, right? Because from each open loop pole, which is non-repeating, we can have only one branch of the root locus which can start, right? So consequently, if we have a open loop pole which is non-repeating, there are only two possibilities. What are the two possibilities? The possibility is that like it can either go along the positive real axis or it can go along the negative real axis. Okay, I hope it is clear, right? How we eliminated the other choices. Okay, so once again, let me state the facts in a sequence. Suppose, let us say we have a non-repeating pole on the real axis and we want to reason out in which direction the corresponding root locus branch will start. If it is going in any direction other than the real axis, we will have two branches starting from the same open loop pole which is non-repeating. But that is not possible. So consequently, we eliminate the possibility of having two branches which go into the complex plane from a non-repeating open loop pole. And so only possibility by elimination is that like the loop locus can go only along the real axis. But now the question is, we are not yet done, right? Because the root locus branch which starts from -4 can either go right side as an option 1 and or left side as an option 2. Now the question becomes, like which side does it go? Okay, so that's where step 2 helps. So what is step 2? So if we look at step 2, we locate the root loci that lie on the real axis. Okay. So what is the step? Let me read this step. This is determined by the open loop poles and zeros that lie on the real axis. We choose a test point on the real axis. If the total number of the real open loop poles and real open loop zeros that lie to the right of this test point is odd, then that point lies on the. Okay, so that is why we look at this condition. Okay, so what we are going to do is that like we are going to reason out this condition in the next class. But however, in the intervening time, please think through the steps. Like why we have written the statement the way it is. Okay, I would suggest that you always start from the two conditions, the angle condition and the magnitude condition, because those are the conditions we use to plot the root locus. Okay, so think about the angle condition and the magnitude condition, and reason out why we wrote down, why we step 2 has been written down the way it has been, okay, given, okay, in that document. And then we will figure out how do we construct or locate the region of the root loci that lie on the real axis. Okay, so that's something we will continue in the next class. Fine. Any questions on what we discussed today?
No, sir.
Okay. So please go through this document, which is available in the classroom folder, and we will continue from here in the next class. Thank you.